Sample problem 18.7. The molar heats of fusion and vaporization of benzene are 10.9 and 31.0 kilojoules per mole respectively. Calculate the entropy changes for the solid to liquid and the liquid to vapor transitions for benzene. At 1 atmosphere pressure, benzene melts at 5.5 degrees Celsius and boils at 80.1 degrees Celsius. So we're going to calculate the entropy changes for two different processes. So benzene has the chemical formula C6H6. And we're going to look at we're going to look at fusion first. So the fusion is essentially the process, the reverse of the process of melting. Okay, so the heat of fusion, FUS, not formation, but fusion, is 10.9 kilojoules per mole. It's positive. Melting a solid into a liquid is generally an endothermic process, so the sign of that change in enthalpy is positive. Now here's what we're going to do. We're going to claim that at the melting point, or the freezing point, we'll call it F for freezing, if the temperature is at the freezing point, this process becomes reversible. Okay? If it's reversible, that means that delta G is equal to 0. We're right at the stage where a little bit of energy in can melt it, a little bit of energy out will freeze it. So it's right on the cusp of being spontaneous or non-spontaneous. Now remember, delta G is equal to delta H minus T delta S. So similarly, what we can say is that if delta G is equal to 0, then we can add T delta S to both sides. And that would be equal to delta H, right? If 0 equals delta H minus T delta S, add T delta S to both sides. You'll get delta H on the right side and T delta S on the left. So if we want to know what the change in entropy is for this process, all we have to do is divide both sides by the temperature. Okay? This goes for any phase change, any change of state process. So this would be true for fusion, but it would also be true for vaporization. It's just the values would be different. Okay? So let's try it for fusion first. That would be 10.9 kilojoules per mole divided by the freezing point, the temperature at which it melts or freezes at, which is 5.5 degrees C. But we need to have that in Kelvin, so we're going to add 273, and that'll be in the units of Kelvin. Okay? Now, actually, let me point out that typically entropy values are reported in joules per Kelvin mole. So I'm just going to multiply this by 1,000 joules per kilojoule just to get it out of kilojoules and into joules. Okay, so 10.9 times 1,000, so it's 10.9 times 1,000 equals, and then we're going to divide that by 5.5 plus 273, and you get 39.1. And then that would be joules per kmol. Okay, so it's really just a little trick of algebra, how this works out. Let's try the second part. The second part, so this is for fusion, melting. Let's try it for vaporization. Again, the change in entropy at the boiling point would be delta H over T. Now the heat of vaporization, or the enthalpy of vaporization, is given in the problem as 31.0 kilojoules per mole. And then the temperature is given as 80.1 Celsius. So we'll add 273. You could argue that we might want to add 273.15 if you want to do that. That's perfectly fine. Okay. Again, we're going to convert it to joules per Kelvin mole because those are the units that entropy are generally quoted in. So 1,000 joules per kilojoule. Okay, so that'd be 31,000, right? 31.0 times 1,000. Okay, divided by 80.1 plus 273. And you get 87.8 or 88. So there's your delta S of vaporization, and this one was delta S of melting. Okay, so in other words, the amount of entropy change that occurs when we melt benzene is an increase in entropy of 39.1 joules per K, if it's 1 mole. If it's 1 mole of the liquid benzene, then vaporizing it, boiling it into a gas, would increase its entropy by almost 88 joules per Kelvin.